Hello students, welcome to the session. In this session we are going to see the last three theorems in the chapter 1. Okay. So before getting into the theorem, we have to recall what are called rational numbers and its types. Okay. So what are called rational numbers? If a number that can be represented in P by Q form, where P and Q are integers and Q is not equal to 0, then it is known as rational number. Okay. Then what are its types? It is broadly classified into two types. One is a rational number having terminating decimal value, and the second one is rational numbers having non-terminating recurring decimal values. Okay. So here the word recurring means repeating. Okay. See, let's see few examples of these types. For example, 3.283. After the decimal point, exactly there are 3 digits. So the digits are ended. So this lies into the category of terminating decimal. Okay. For example, see this number 2.142.142.142, like that it goes on. So it is non-terminating and it is repeating, right? See these series of digits 142, 142, 142. So I can simplify it as 2.142 bar. Okay. So this example lies into the category of rational numbers having non-terminating recurring decimal values. Okay. Students, here I have written few examples for the rational numbers. Then I am going to find the decimal values of these numbers and going to categorize these numbers into either terminating decimal values or non-terminating recurring decimal values. Okay. Let's see. The first one, 5 by 2. Here the quotient will be 2.5. Okay. So the decimal value here is 2.5. See, after the decimal digit there is exactly only one digit. So it lies into the category of terminating decimal. Okay. Then second number, 8 by 15. So the quotient will be 0.75 goes 5 times and then 5. So it goes for 3 times and again 5. So it goes for 45. So 0.3333 etc. So the decimal value is 0.53333 and like that it goes on. So see here, it is a non-terminating recurring decimal. Okay. Then third value, 17 by 5. So here I will get 3.4. So 3.4, it is a terminating decimal. Okay. Then 17 by 6. Here 12. So it's 2, 5, 48, 2.8, then 0, so 8, 2.83, 2.8333. So it is 2.833, like that it goes on. So it is a non-terminating recurring decimal. Okay. Then next example, 9 by 20. Let me divide the number 9 by 20. Here the quotient will be 80. So it's 4 times 0.45. Here 0.45. So it lies into the category of terminating decimal. Okay. Now we are actually dividing the given values and then telling whether it is a terminating decimal or non-terminating recurring decimal. So imagine you need not to divide the given values. Without dividing itself, you can say whether it will have a terminating decimal or non-terminating recurring decimal. So the trick is that you have to see the denominator. Okay, first see the number carefully whether it is in most simplified form or not. Here I have taken the examples which are all in its most simplified form. Okay, so I have to take the denominator directly. Here the first one is 2. Prime factorize the denominator. By prime factorizing 2, I will get 1. So it can be written as 2 power 1. Okay, here the denominator is 15. Prime factorizing the numbers is 15. I will get 3, 5. Okay, so it is 3 into 5. Then in this example 5. So 5 is written as 5. Okay, then 6. 6 is written as 2 into 3. Then 20. 20 is written as 2 square into 5 power 1. Okay. See here, I am writing the denominator as the product of primes. Okay. So the 5 by 2 has the denominator in the form 2 power 1. So it is a terminating decimal, and here 5 power 1, it is also a terminating decimal, and here 2 power 2 into 5 power 1, it is also a terminating decimal. So if I am having a rational number in the form p by q, where both p and q are co-prime numbers, then the q, the factorization of the q is either in the form 2 power m or 5 power n or 2 power m into 5 power n. Then I can say the decimal value of the number will be terminating. Okay, see, we have to pick the denominator and prime factorize the denominator. If it is expressed in the form of product of primes, then look at the form whether it has either 2 power m or 5 power n or 2 power m into 5 power n. If the product of primes lies in any one of these categories, then I can say that it will be having a terminating decimal value. Okay. So if it is not in the form 2 power m or 5 power n or 2 power m into 5 power n, so it means that other than 2 and 5. So if the denominators having factors other than 2 and 5, then definitely it will be a non-terminating recurring decimal value. See here, it is having factors other than 2 and 5. 5 is present, but 3 is also present. So factors other than 2 and 5 are present here. Okay. Then this is a non-terminating recurring decimal. Then see this, here 3 is present. So factors other than 2 and 5 is present here. So it is a non-terminating recurring decimal. Okay. So I can conclude that if it is not in the form 2 power m or 5 power n or 2 power m into 5 power n or other than the factors 2 and 5, then it will be a non-terminating recurring decimal. Students, see these examples. Now we are going to categorize these examples into either terminating decimal or non-terminating recurring decimal without actually dividing. Okay. So there is only two steps. Okay, there are only two steps. The step number 1 is make the number to its most simplified form. Okay, so you have to make the given fractional number into its most simplified form. If it is already in most simplified form, then leave it, leave the first step. Okay, then in second step, pick the denominator and express it as the product of primes. So students, in your second step you have to pick the denominator and express it as the product of primes. Okay, so let me try with these numbers. First one, 28 by 32. See whether it is in most simplified form. No, so it can be cancelled, right? So it can be cancelled in 4 table, so it is 7 by 8. Now I am having the value 7 by 8. Now it is in most simplified form. Okay, now pick the denominator. Denominator is 8. So prime factorization of 8 gives 2, 4, 2, 2, 2, 1. Okay, so I am getting it as 8 is equal to 2 into 2 into 2, that is 2 power 3. Okay, so in second, 13 by 7. See, 13 by 7, it is already in its most simplified form. Now pick the denominator. Denominator is 7. So 7 is a prime number, so it is divisible only by 7. So 7 can be written as 7 power 1. Okay, so in third example, see here, 48 by 96. 48 by 96. Yes, it can be cancelled. It is 1 time, it is 2 time. Okay, so it is 1 by 2. So 1 by 2, pick the denominator. It is 2. Prime factorization of 2 is 2, because 2 is a prime number. It can be only divided by 2. So 2 can be written as 2 power 1. So students, we conclude the theorems given in the textbook. Okay, so theorem 1.5 states that if x has a terminating decimal value, for example, let x is equal to 0.4. So it has a terminating decimal value. Then this x can be represented in the form p by q, where p and q are co-primes and q is in the form either 2 power m or 5 power n or 2 power m into 5 power n, where m and n are non-negative integers. So let us try. So 0.4 can be written as 4 by 10. On simplifying this, 2 by 5. So I am writing it as 2 by 5. Here both 2 and 5 are co-prime numbers, right? So these two numbers are not having any common factor other than 1. So 2 and 5 are co-prime numbers. So it can be written in the form p by q, where p and q are co-prime numbers. Then q is in the form, that is 5. 5 is in the form. Here 5 can be written as 5 power 1. So it is taking this condition, right? So it is in the form 5 power n, where n is non-negative integer. Here n is 1. So it is a non-negative integer. So this is the theorem. Okay. So if x is a terminating decimal value, then it can be written in the form p by q, where both p and q are co-primes and the prime factorization of the q is in the form either 2 power m or 5 power n or 2 power m into 5 power n. Here in this example I am having 5 power n. Okay. Then the theorem 1.6. So the theorem 1.6 is just the inverse of theorem 1.5. Here I am going in the reverse order. Okay. So for example, take the number 2 by 5. Let x is equal to 2 by 5. So x is in the form p by q, where both p and q are co-primes and the prime factorization of the q is in the form 5 power 1, right? So it can be substituted as 5 power n, where m and n are non-negative integers, then definitely it will have a terminating decimal value. If a number is given with these conditions, then the decimal expansion of this value is terminating decimal value. This is the theorem 1.6. okay, it is just the inverse theorem of 1.5. okay. So here in the previous theorem 0.4 is represented as 2 by 5, here 2 by 5 is represented as 0.4. okay. Then the last theorem, theorem 1.7 states that if x is in the form p by q where p and q are co-primes and q is not in the form of either 2 power m or 5 power n or 2 power m into 5 power n, then it will have a non-terminating recurring decimal. Okay. So they are given that if x is represented in the form p by q where p and q are co-primes. For example, let me take a value 8 by 15. Okay. Here both x is represented in the form p by q where 8 and 15 are co-primes, which means that they are not having any common factors other than 1. okay. Then q is not in the form of 2 power m or 5 power n or 2 power m into 5 power n. Here prime factor is the number 15. I will get, so 15 is represented as 3 power 1 into 5 power 1. So it is not in any of these forms. okay. So 15, the denominator value is not in any of these forms. So definitely it will have a non-terminating recurring decimal. okay. So previously I have seen that the 8 by 15 value is 0.5333, like that it goes on. So it is having a non-terminating recurring decimal. So this is the proof of the theorem 1.7. If a number is in the form p by q where both p and q are co-primes and q is not in the form in any of these forms, then definitely it will have a non-terminating recurring decimal. okay.